Hi, this video is on section 9.2, and we're going to go over the critical value approach to hypothesis testing. So in this chapter, we'll be working with two different approaches to hypothesis testing. The first is this critical value one. I have here on the board I just cleaned it up just a little bit, just to overview what we did in the previous video. Is we knew that X bar had a normal distribution because its parent was normal, right? The parent population of the bags of pretzels had a normal shape. So the distribution of X bar is normal. And under the null hypothesis, it has a mean of 454 grams. And sigma sub X bar is sigma over the square root of n has 1.56. That's the value of sigma sub X bar. And so what we did, and in the previous section, was we took the 450, X bar was 450, and we had made the decision that we were going to reject the null hypothesis and recalibrate that machine if the sample mean was more than 2 standard deviations away from the null mean. So we set this up like a chapter 7 problem, right? Where we have an understanding of the distribution of the sample mean. We have an observation 450, and we put it on the z-bus, and we come out and we get it at negative 2.56. Okay, so we rejected the null hypothesis because negative 2.56 was outside this region that we had agreed on, and we could have agreed on it, made a different agreement about when to bring those machines down, but this is what we have. Okay, this is what we decided before we looked at the data. So there's some terminology I wanted to go through. We have the test statistic. So the test statistic is z equals X bar minus mu naught divided by sigma over the square root of n. So mu naught is the null mean, right? And under the null hypothesis, which this calculation is being made with assuming the null hypothesis is true, then this z-score is a standard normal, okay? So this was our test statistic. Our rejection region was the area, the set of values for the test statistic, that leads to the rejection of the null hypothesis. So our rejection region was anything less than -2 or greater than +2. So I'm going to indicate this here with rejection. I'm just going to note it. The rejection region is actually a 2-part region. It's a 2-tailed region, which makes this a 2-tailed test. So there's our 2-piece rejection region. We would reject the null hypothesis if my test statistic came out over here, less than -2, or if my test statistic was greater than +2. Okay, the non-rejection region is the area of the set of values of the test statistic that leads to non-rejection of the null hypothesis. So for our example, we had agreed that it was going to be if my test statistic was between -2 and 2 that I would not reject. So this becomes the do not reject region. This -2 and 2, they are called the critical values. Doesn't usually happen, but if you would actually calculate a z-score and come up with exactly on the dot the 2, then you would be part of the rejection region. So the critical values are formally part of the rejection region. Okay, so looking at the notes, we see that we have some definitions here, which we just went over. And then the sign, just these, so what's going on here are, I've just laid out all the important values, definitions, that are needed for the critical value of hypothesis testing. Test statistics, rejection region, non-rejection region critical values. We just went over that at the board. We had a discussion in the previous video regarding what is the sign of the alternative hypothesis. And we saw that when we were using the not equal sign, we were doing a two-tailed test, and that both of those tails, both sides of those tails are the rejection region. If we were doing a left tail test, then our rejection region would just be the left tail, or a right tail test, the rejection region would be the right tail. So here are the possible conclusions. We can conclude, if the null hypothesis is rejected, that at the, let's see, alpha significance level, we say a test is statistically significant at the alpha level. Now I will provide the alpha level to you, but we say that the test is statistically significant at the alpha level if you set up the rejection regions to have a total area of alpha, and I'll show you how to do that in just a moment. And then here would be the conclusion. At the alpha significance level, the data does provide sufficient evidence to reject the null hypothesis. And we'll state that in the context of the application. If the null hypothesis is not rejected, we conclude that the data do not provide sufficient evidence to support the alternative hypothesis. We say that the test results are not statistically significant at the alpha level, and we never accept the null hypothesis. So a way to interpret the test, which is something we will have to do for every hypothesis test, is that at the alpha significance level, the data does not provide sufficient evidence to conclude the alternative hypothesis. All right. So our job here is to be able to determine the critical values and the rejection, non-rejection regions, given the significance level of the test. Okay. So what we want to go over here is for each kind of test, we can have a left tail, a two tail, or a right tail. We want to be able to identify these delimiting values here, which give us an alpha area in the critical region, or another word for critical region is the rejection region. All right. So he's very interested in this whole hypothesis testing today. Okay. So we're going to determine what those critical values are, z sub alpha or z sub alpha over 2. And I'm going to go over to the whiteboard, and we're going to just go through some examples on how to determine the rejection. Okay, so I just want to go over a couple of examples. We'll look at the two-tail alpha equals 0.05. So on a two-tail test, we have a standard normal. This is a standard normal. And we want to find the two delimiting values that give us a total area of the rejection region of 0.05. So each tail then has to have alpha over 2 in it, right? Or 0.05 divided by 2, 0.025. And that tail, and then this tail also 0.25. So the total is 0.05. And so the question is here, we will call this z sub alpha over 2, right? So that's alpha over 2. And we're looking for this value of z that has the property that 0.025 is to the right of it. And of course, we know it's going to be the negative of the z that has the property that has 0.025 to the left. So grab your formula cards. Okay, so coming on over to the formula card, we know that what we can do is we can do the indirect lookup over here. Okay, and we would look for say, we can look for 0.02 in right tail, right? Or we can take a little shortcut. I think I showed you guys this a little bit last week. Is that if we go to the bottom of the T table, we have this little table down here, which is mostly all the important values of for the normal distribution. Okay, so we are looking for, make it big enough for me to actually see it. We're looking for Z, so 0.025, and we see that it's 1.960. Okay, so we see here that this would be 1.960, and this is plus minus 1.960. That's a value we've seen before. We know that the normal curve looks like this. So these would be our critical values, negative 1.96 and positive 1.96. Let's go over to the other side here and do a left tail when alpha equals 0.05, okay? So we'll draw the picture of that. And again, this is a standard normal. And we're looking for this delimiting value, it's left tail, that has the area that 0.05 is to the right of it. So this is going to be, the delimiting value here is going to be actually negative of the 0.0, so of the Z sub alpha, right? Z sub 0.05. So let's go ahead and look back at the table. So take the formula cards out, please. And you see here that we can come down here and find 1.645 Z sub 0.05. So we know that 1.645 would give an area of 0.05 to the right. So we're going to take its negative. And that's our critical value for a left tail test with alpha equals 0.05. Okay, so we really now have a lot of pieces, and I know they feel like not quite integrated yet. So they're sort of all over. We have test statistics, rejection regions, null and alternative hypotheses. We have conclusions for decisions. And so I'm going to stop the video here. And in the next video, I'm going to go through one example from beginning to end. And that's going to be like really show you how to do a hypothesis test.